Today I'll be talking about graph analytics and xGT and what that means, how you do it, and how xGT helps you do that. So we'll start out with sort of a basic idea of what graph analytics is and how it differs from normal data. A lot of times what you see will determine what you ask. In biology, they have a lovely phrase, structure dictates function, which describes how proteins interact with their environment around them. So how they're built affects how they interact with the cells and the job they do. I'd like to say data science works a lot the same way, in that how you represent your data affects what questions you ask about it and sort of what sense you can make of it. So if you take this data here, you see information that we have in tabular form, a bunch of dates, some numbers, values. Don't necessarily know what it means. But when you express it this way, you might ask questions like, what's the maximum value in a certain cell, certain row, take a mean across a column, give you some idea of what the values are with respect to how it's organized in tabular form. But this isn't the only way to represent data. There's plenty of different ways. And the way we represent data at Tavares is with graphs. It's the same data as before, same organization, same values, just represented differently. And here we can ask different questions and get different conclusions. For example, this node over here named 3, it has a high out degree, it's lots of connections to other nodes. You might not necessarily have seen that in the tabular form, different representation. Same with this disconnected pair of green nodes, 4 and 7. It's hard to see that when it's laid out in a single table. So when you represent your data this way, you get more power in terms of what you ask and what you figure out. Property graphs are an extension of that. So it's taking that topological structure that you organized from the data before and adding attributes or properties to those elements. So in this example, we have a vertex and an edge. That's the connection between this data, but it can also carry properties, these dates or floating point numbers we've associated with both the vertices and edges of the graph. And this kind of gets the best of both worlds, right? We have the structure of the graph itself, which you can ask connectivity questions, who's connected to who, how do you get from A to B, and you also have dense attribute information that lets you ask questions about what that data is. So once you get from A to B, what does B look like? What kind of stuff is there? So during this presentation, we're going to go through and figure out how xGT helps you analyze graph data. The running example we're going to be using, however, is that of cybersecurity. So what we have here is a data model. The data set here is an anonymized network traffic data set. It was collected by Los Alamos National Labs, a project they had there to analyze the internal traffic amongst their enterprise network. And they released this paper on it, they anonymized it all, so all the devices are given random numbers. But all the traffic's there, so you have net flow data, packets shooting from one node to another, and you also have a bunch of Windows events that are recorded at each machine. And so that's what we see here. We have network traffic up in this first row, you have a source and a destination, every one, and then you have the event logs, which are a bunch of fields, and then a machine associated with it. And that creates our graph data model. So we combine all of these things. Every time you see a reference to a particular machine, you'll associate it with a specific vertex in the graph and link it up. So if a packet shoots from one machine to another, and then another packet shoots from that to somewhere else, you see this connectivity in the graph. And so we're going to be asking analytic questions about what's in that data, how does it look when you look at it and represent it as a graph. First, I want to talk a little bit about what graph analytics means and what kind of questions you might ask now that you have a different representation of the graph. So the easiest one is local structure. Simply, now that you have connections between things, what does it look like? Who's connected to who? What's the neighborhood of some vertex? What's around it? This is fairly easy to look up once you have the graph structure, right? You point it at a specific place and poke around. Follow all the edges that are leading from there to there. But you can start asking more complicated questions too. Whole graph algorithms is one of them. This is sort of the traditional graph theory realm from academia. And you can ask things about global metrics of the graph, how connected things are in a holistic sense. You can also ask questions that describe what paths look like in the graph or how you might rearrange the graph to get a certain property in terms of cuts or groupings and things. And finally, you can ask things about patterns in the graph. So if I have a specific entity or idea that I'm looking for, then I can go through and look through this massive set of connections and try to pull those out. And graph pattern matching is really where xGT shines, and that's kind of the point of the tool. We liken it to finding structural needles in graph haystacks. The idea being that without representing it as a graph, you have no opportunity to find these kinds of patterns at scale. So to go back to our running example, we had our data set, we have a data model, now we've represented it as a graph. What kinds of things can we ask about it? So the example we're using today is to identify botnet call home behavior inside this data set. So imagine you have a couple machines that are infected with some malware and they want to call back home to their command and control network. When they do that, they leave a trail, right? They leave evidence that they've been in a certain place. So the communication out to some exfiltration node is logged as a net flow event. That communication out to an external IP is logged in an event. And you can find these patterns in the data. The nice thing about graph patterns is they're fairly intuitive to express, right? So you represent the idea that when you restart a machine, the malware starts up with it, and you can just draw that out. And then you say, okay, well, once it starts up, that needs to communicate to somewhere else. You draw that as an edge to some arbitrary node somewhere else. And you build these iteratively to make the query more complex step on step. One of the challenges with graph pattern matching is that computationally it ends up being a very difficult problem to do. And this comes from two places. One is a theoretic problem. In graph theory, this problem is called subgraph isomorphism. It's matching little pieces of graphs with other pieces of graphs. And the problem is unfortunately NP-complete, which means that if you're designing an algorithm to solve it, there are certain limits that you have to abide by, and they're always going to be somewhat expensive. The second problem, it has to do with the way graphs are laid out in memory. When you represent a graph, the connections between two vertices can end up being anywhere in memory. So if you are starting at node A and you're trying to jump to its neighbor B, A and B may not be next to each other in memory. And when you make that kind of hop, it tends to be fairly costly for modern computer architectures. And this really derives just from the fundamentals of the problem. When you have a simple pattern like A, B, and C, what you're actually computing is this massive exponential search space, right? For every possible vertex in your graph, you have to consider whether that would be a good match for A. And for every neighbor for every one of those vertices, you have to consider if that would be a good match for vertex B, and so on and so forth. So the more topological constraints you have in your problem, the larger the search space gets, and the more expensive the problem becomes. And this is really why we designed xGT. The point was to design a tool that was efficient at solving these known theoretically hard problems and productive for data scientists in practice. And that's what we see. So one of the sort of four keys of our product end up being scale, which is we operate on the largest memory sizes you can get in a machine. So it's easy for us to handle tens of terabytes of memory. Speed, we are designed for modern parallel architectures, so we take advantage of many-core processors. Scalability tends to be fairly linear up to the largest sizes. We have no problem with single machines, tens of terabytes of memory with thousands of cores. And then with respect to productivity and complexity, we've designed a system that you can express a graph pattern fairly easily. You just describe what you want in terms of here's a vertex, here's an edge, they should be connected in this way, here are the constraints. You figure out how to solve it, and xGT will look at it, analyze it, and compute the best, most efficient way to solve that. And that really gets down to probably the most important, at least from a data scientist's point of view, aspect of this, and that's productivity. At the end of the day, time to solution is the name of the game, and so xGT intends to cut down the cycle of analysis from asking your first exploratory questions to getting some insights to folding that knowledge back on the original questions to ask more specific ones. It's important for that cycle to take as little time as possible to make sure that the data scientist is getting the most out of their day and the time they put in. One way we can judge the raw performance of xGT is with a benchmark called temporal triangles. This is a simple synthetic performance benchmark that we've invented just to demonstrate the performance implications of what graph pattern matching looks like. The pattern itself is a simple 3-vertex, 3-edge pattern. So the topology is a simple triangle. A talks to B, B talks to C, C talks to A, in that order. And all of these messages have to occur in time order. So T0, T1, T2, in that order, within a specific time window. This turns out to be surprisingly hard for conventional data science tools. When you're using a bulk parallel tool like Hadoop or any kind of MapReduce engine, they tend to use an approach for solving these that involves producing all the possible answers and then filtering back which ones don't make any sense. The intermediates that are generated in this tend to be very expensive, and the time that it takes to generate them tends to be very long. xGT uses a different approach. It's a little bit more dynamic. We produce partial answers in smaller sets, on demand as they're being computed, and filter them aggressively. And that results in much, much smaller intermediate sets, and at the end of the day, a much shorter computation. Here's an example of a run of temporal triangles on xGT and one of our graph database competitors. So here we're measuring the time, total time in seconds, so lower is better. And on the x-axis, we have the number of edges in the graph that we're talking about. So 100 million edges on the left-hand side, up to about 2 billion edges on the right-hand side. This simple 3-edge, 3-vertex query starts bringing some of the traditional tools to their knees. So we see at 2 billion edges, we're spending several days worth of compute time to figure out this answer. And xGT can churn out this answer in just about 12 minutes. And we see this fairly consistently across different queries. Moreover, the more complicated your query gets, the larger that combinatorial search space becomes, and the more pronounced this difference becomes. So we see as you get more complex, we tend to do even better in terms of the performance separation. So now we're going to do a demo of the product. This is a Jupyter notebook. It's running Python 3, an Anaconda version, and we have a Amazon EC2 instance set up with xGT connected somewhere in the cloud. And so all we're going to do is connect from this laptop out to the cloud on the server and demonstrate how you might load some data, model it in a graph representation, and then ask some questions of it. Same cybersecurity example that we've been running through in the slides. So first, all we're going to do is use the normal Python tools. Our Python client is up on pip. You can download it today. Pip install xGT works out of the box. So we'll run that, demonstrate that xGT is indeed running up on some EC2 instance in the cloud, and we'll establish a secure tunnel to communicate to it over the web. Importing and connecting to xGT is fairly simple. Import xGT, connect to it. And then the first step we're going to do is look at that data that we had and then create a data model. xGT is strongly typed, which means that every field and element and piece of data that we have is defined by some schema that has well-known data types. And so that diagram that we showed earlier about the graph model, the one we see here, is just replicating that, and we're going to try to describe that in code form. So if we go down a little bit, first thing we're going to do is create a frame. So if you're a data scientist, data frames should be fairly familiar to you. We have analogs for graph elements, so vertex frames and edge frames. Exactly the same structure as a data frame, they just represent graph object as well as properties. So we'll describe them here, we'll create a schema for it, and declare that these things represent the devices in our cybersecurity data set, and that's this statement here. And then we're going to describe two types of edge frames, one for NetFlow data, and that's this one here, which captures both the source and destination, but in addition it captures things like the size of the packet, the protocol that was talked over, information that we might need to capture the patterns that we're looking for. And then likewise we're going to describe an edge type that represents the Windows event logs that we're going to load in. And so this has, again, the machine that's the event was generated on, but also a bunch of information about what that event is, who did it, what the process was, what the parent process was, that kind of thing. Once we've described the structure of the data, that graph model, then we can actually load the data in. And so this can be done through a variety of mechanisms. You can take it off disk, you can go over URLs, you can grab it from S3. And once we load the data, and in this case, we're going to be loading about 16 million edges, these are pre-computed. The total time for loading that data in was only 4 seconds. We'll load the NetFlow data in the same way. Give it a URL, it'll pull it from wherever the resource is located and load it up. Again, this NetFlow data that we're going to be using today is about 200 million edges, and the total time to load this thing in was just under a minute. Once we get the data in, then we can ask questions about it. And this is going to go back to that running example that we had earlier about trying to find botnet behavior. So the query is described here in its full form. But the way we're going to actually run it is describe it and build it up iteratively as if a data scientist was actually trying to look for it. So you might start with something that says, okay, just find me the smallest part of this pattern that I know about. In this case, it might be the restart of a machine. So you know that once a machine restarts, it's got to boot up. There'll be an event log for that. It's going to start some program, which represents the malware. And then it's going to communicate back through 2 hops to get to its command and control network. So the first thing we're going to do is search for just the boot events. And these are going to be found amongst the several million Windows event logs that were loaded into memory before. And we're just going to search through all of them. This is a fairly easy search any kind of MapReduce or bulk parallel data analytics tool will be able to do the same thing for you. So the language we're going to use for doing this query is called Cypher, or TQL, which is our version of it. It's just adding strong types to the language. It's declarative query language, so you describe in terms of what the answer you're looking for is, and then you feed it to the engine, and it'll go looking for that pattern. And what you see here, this statement that says match and where and return, is just a description of this graph pattern here. So we're looking for a vertex A, and it has a single boot event tied to it that it's going to look for. Run over tens of millions of edges, come back. This took less than a second to compute. Afterwards, we're going to look for a slightly larger set of that pattern. So now we want the boot event and the start of the malware. And again, we're not only looking for these topological parts where there's edges that reflect the event logs, but also some property constraints on them. For instance, the program might have to have a specific ID, or the time between the restart and the program start has to be within a certain window. If you see it somewhere else, perhaps it's not the right malware, perhaps it's not associated with command and control behavior. So we run that. Again, not a very difficult query, only one edge. There's really no graph representation going on here. Any bulk parallel tool can do this, and we'd be competitive with them. These answers are coming back pretty quick. Once we start with the graph part of the query, so when a single vertex is communicating to somewhere else, that's where it starts to get more interesting, because you have this explosion in different types of matches. So here we're describing that both that boot event and the program start, and then there's going to be some communication with packets flowing from vertex A to vertex B. And again, described in a declarative way. So we describe the structure up in this match statement, and then the properties that we wanted to constrain in the where clauses, and then return the answers in terms of a list of matches of A's and B's that we found in that data. Now we're fusing two data sources. So we have the event logs and the NetFlow data, and now we're searching through not just the tens of millions of event logs, but also the couple 100 million NetFlow logs we have. In a combinatorial sense, this is probably on the order of 10 to the 12th possibilities that we have, and we have to filter down to the ones that match our desired pattern. In this sense, after you do this query, we have 109 possible matches for this partial query. And over this couple 100 million events, 5 seconds. Finally, we can get to the full query. So now we're doing 2 hops to the network, the same program start and machine restart. Same query, but a couple more topological constraints and a couple more property constraints on the new NetFlow edge now. We got to make sure that NetFlow 2 comes temporarily after NetFlow 1. Again, that combinatorial explosion is going to get a couple 100 million worse on a multiplicative factor, because we now have another hop that could be a possible part of the answer. So we'll take those 109 partial answers, and there's going to be more that exist now in the final result. In here, we've discovered 981, and the entire query, searching over all those hundreds of millions of edges, 12 seconds. And this goes back to that point about the scaling of xGT. In a tool like Hadoop or any other MapReduce infrastructure, you're going to see much steeper scaling in terms of the time it would take to grow from the partial patterns that we described earlier to these full patterns at the end. Data analysis is a very broad problem, and so data scientists tend to use a variety of tools depending on what problem they're solving at any given point in time. We understand that xGT and graph analytics in specific is only one of those problems they have to solve. So we anticipate that when someone sits down to use xGT to solve their graph analytics problem, there's going to be a half a dozen or a dozen other tools that they're going to have to interact with in order to process their data, analyze the results, or just ask a different question in a different way. So we expect that xGT works with these. Upstream, you might have data filtering tools, things that clean or eliminate bad data that you want to feed into the graph. Perhaps you are taking raw data and turning it into something formatted. Downstream, you might take the results of your graph analytics and put them into some visual analytics tool to see what it looks like, to get some sense of what the highlights are. Or you might even have actionable alert systems, so that when some analytic completes, it flags a specific behavior or piece of data that you might want to take a certain behavior on. And finally, you might have complementary analytics. So things like you might want to run a machine learning algorithm to classify certain properties, tag certain vertices, understand the data in a different way, and then look for graph patterns. Or vice versa. Take the results of your graph pattern search and then classify the answers in a certain way, or understand or predict something about those results. It's all part of a larger ecosystem, and we anticipate xGT is going to be a productive part of it.